Okay, let's start today's class. Today, let's have a look at lesson 3 of chapter 1, Limits and Continuity, part 2. So first, let's have a look at today's learning goals. After this lesson, you are expected to understand the definition of one-sided continuity of a function at a point. Understand the definition of continuity of a function on an interval. Recognize common functions that are known to be continuous. Use function continuity and limit properties to algebraically evaluate one-sided limits or limit, if exists, for a function at a certain point. And last, apply limits to analyze real-world problems. Okay, remember that yesterday we have talked about the continuity of a function at a certain point, right? And we have also learned the left limit and right limit of a function at a point. So similarly, we can also define the left continuity of a function at a certain point, A, or the right continuity of a function at point A. In definition, we say a function f is left continuous at point A if the limit of this function when x approaches A from the left side equals the image of this function at this point A. And we say the function is right continuous at a point A if the limit of this function as x approaches A from the right side equals the image of this function at point A. If the function f is continuous at A, then it is both left and right continuous at A. The above definition regarding left or right continuous functions is illustrated with the following figure. So for example, let's have a look at the figure on the left. In this figure, at point A, we can see that when x approaches A from the left side, such as from this direction, then we know that the limit of this function as x approaches A from the left side equals the image of this function at this point, which is this point here, right? Therefore, we say this function is left continuous at this point. And in the figure on the right, as you can see here, when x approaches A from the right side, the limit of this function as x approaches A from the right side equals the function's image at this point A. Therefore, we say this function is right continuous at x equals A. You understand? This is a concept of left continuous and right continuous. Okay, then let's have a look at the continuity of a function on a closed interval. So yesterday we have talked about the continuity of a function on an open interval, right? So similarly, we can also define the continuity of a function on a closed interval. So first, let's have a look at the concept here. One-sided limits allow us to extend the definition of continuity to closed intervals. The following definition means a function is continuous on a closed interval. It is if it is continuous in the interior of the interval and possesses the appropriate one-sided continuity at endpoints of the interval. So by definition, a function f is continuous on the closed interval a, b inclusive if the following three conditions can be met. First, it is continuous on the open interval a, b exclusive. Second, it is right continuous at point A. That is, the limit of this function fx as x approaches A from the right side equals the image of this function at this point A. And third, it is left continuous at point B. That is, the limit of this function fx as x approaches b from the left side equals the image of this function at point b. For example, if I have a function like this is our point A, this is point B. It is obvious that, first of all, this function is continuous on the open interval A to B, right? And we can also see that when x approaches A from the right side, the limit of this function equals the image of this function at this point. And when x approaches B from the left side, the limit of this function equals the image of this function at point B, right? Therefore, we say this function is right continuous at point A and left continuous at point B. Therefore, we say this function is continuous in the closed interval from A to B. Understand? And this definition can be extended to continuity on half-open intervals, such as from A to B, A is exclusive, B is inclusive, or from A to B, A is inclusive and B is exclusive. And unbounded intervals, such as from 0 to positive infinity, 0 is inclusive, or from negative infinity to 4, 4 is inclusive, etc. Okay, so this is the concept of the continuity of a function on a closed interval. Okay, next, let's have a look at an example. So this diagram here shows the continuity of a function on different intervals. The function shown on the left is continuous in the following intervals. We can easily verify these conclusions. For example, in the interval from A inclusive to B exclusive, we can say that the function is continuous in the interval from A to B exclusive, right? And then we can see that the limit of this the function is left continuous at point A, right? Therefore, we say this function is continuous in this interval from A inclusive to B exclusive. And for another example, let's consider this interval from B to C exclusive. First of all, this function is continuous in the open interval from B to C, right? And second, this function is right continuous at point B. And this function is left continuous at point C, right? Therefore, we say this function is continuous in the closed interval from B to C. And similarly, let's consider the next interval, for example, from C to D. First of all, this function is continuous in the open interval from C to D, right? And second, this function is right continuous at C and left continuous at D. Therefore, we say this function is continuous in the interval from C exclusive to D inclusive. And you can use the same method to verify the other intervals. Any questions? Okay, so we have talked about the concepts of continuity of a function at a certain point or in an interval, right? So next, let's have a look at the common functions that are known to be continuous. We have the following statement here. All elementary functions are continuous at any point where they are defined. So note here, you need to know what is an elementary function. An elementary function is a function built from a finite number of compositions and combinations using the 4 operations, such as addition, subtraction, multiplication, and division. over basic elementary functions. The set of basic elementary functions includes, for example, first, the algebraic polynomials. We have already talked about polynomials in our previous lesson, MHF4U, right? And second, rational fractions or rational functions. This is also basic elementary function, which is a ratio between two polynomial functions, right? Also, we have learned this type of function in our previous course, MHF4U. Okay, the third typical type of basic elementary function is called the power function, which has a form x to the power of p. The next type of basic elementary functions is called exponential function, with the form of a to the power of x. A is a coefficient. And also, the logarithmic functions such as log base a of x is also a type of basic elementary functions. So note here, the exponential function and logarithmic function are the inverse of each other, right? So in the logarithmic functions, note that the base number a must be greater than 0 and not equals 1, right? And x must be greater than 0. Okay, next we have the trigonometric functions such as sine x, cosine x, tangent x, cotangent x, secant x, and cosecant x. These type of functions are also basic elementary functions. And also the inverse of the trigonometric functions are also basic elementary functions, such as arcsine, arccosine, arctangent, arccotangent, and arcsecant, arccosecant. Also, the hyperbolic functions are also basic elementary functions. And also the inverse hyperbolic functions are basic elementary functions as well. So these functions are continuous at any point where they are defined. Okay, so this is one of the most important conclusions in this lesson. So here, the proof of this statement involves the definition of the limit and continuity. So we won't cover that in this course. You can just treat it like a conclusion here. If you are interested, I can give you a link of a reading materials. You can read that after this class, okay? So these conclusions, this statement is actually proved. For us, you can just use this statement to help you to find the limit of any basic elementary functions or the composition of these basic elementary functions. So this means if we already know a function f(x) is continuous at a point x equals a, then this actually can help us to find the limit of this function f(x) when x approaches point a. Because by definition, if this function is continuous at this point, we know that the limit of this function as x approaches a should equal the image of this function at this point, right? So, for example, if you want to evaluate the limit of this function here, when x approaches 2, so apparently this function is a polynomial function, right? Because polynomial function is a type of basic elementary function, which is also an elementary function, right? For elementary function, it is continuous at any point where they're defined. Therefore, we can use this conclusion to find the limit as x approaches to some single point, right? We can just insert x into that equation to get the limit of this function at this point. Because this function is continuous at that point, the limit of this function as x approaches that point should equal to the image of that function at this point, right? Therefore, we know that the limit of this function as x approaches 2 should be the value of this function at x equals 2, right? So the limit of this function at x equals 2 should be 3 times 2 raised to the power of 4 minus 5 times 2. Understand? So this gives us 3 times 2 raised to the power of 4 is 16 minus 10, and 48 minus 10 gives us 38, right? Do you understand? Any questions? No? Okay, then let's see another example. So let's consider this example here. So this time, this is actually a rational function, right? As we said, rational function is also a elementary function. So the limit of this function as x approaches to a single point should equal the image of this function at this point, right? So probably you want to insert x equals 1 to this expression. So let's see what you will get if you insert x equals 1 there. So if we insert x equals 1 to the numerator, that'll give us 1 minus 6 plus 5. And if you insert x equals 1 to the denominator, this will give you 1 minus 3 plus 2. Then you will get a expression like 0 over 0, right? So what is this value? This is very difficult to evaluate, right? Because we don't know whether it's 0 or some other things, right? So before you do that, if you have a rational function or something like that, try to simplify that first, okay? So if this won't work, always try to simplify your expression before you evaluate the limit. So in this case, we evaluate the limit of this function when x approaches 1. So note here, the numerator can be factored to x minus 1 times x minus 5, right? You can use a cross multiplication method. This is very easy to factorize. For the denominator, this can be factorized to x minus 1 times x minus 2, right? Understand? And because we are evaluating a limit of this function when x approaches 1. So note here, when x approaches 1, x is actually a number that is very close to 1, but cannot be 1, right? Therefore, x minus 1 is actually not 0. We can just cancel this term in the numerator and denominator. So that becomes, we are trying to evaluate the limit of this function as x approaches 1. Right? So now we can insert x equals 1 to this expression, because this expression is also a rational function, right? For a rational function, it is continuous at anywhere that this function is defined. Therefore, the limit of this function at a single point should equal the image of this function at this point. Therefore, we say the limit of this function as the x approaches 1 is 1 minus 5 over 1 minus 2. So this time we won't have an expression like 0 over 0, right? Therefore, we can simply evaluate its limit as -4 over -1, which is 4. You understand? Okay, so let's make a summary here. So for the previous example, if you want to evaluate an expression like this, note here, if we substitute x equals 1 into the equation, we'll obtain the indeterminate form 0 over 0, right? This is called indeterminate form because We don't know what this what value it is. This function is not defined at this point. However, it is not necessary for a function to be defined at x equals a for the limit to exist. The indeterminate form only means that the limit cannot be determined by substitution. We must determine an equivalent function representing x for all values other than x equals a. One way of addressing this situation is by factoring to create an alternative form of the expression. In doing so, actually we are removing the indeterminate form so that the limit can be evaluated through substitution. This function is said to have a removable discontinuity. So if you draw the diagram of this to draw the graph of this function, so note here we have already learned how to draw the graph of this function, right? It's a fraction between two linear functions. First of all, x cannot be positive 2, so you have a vertical asymptote here, right? Next, the value of this function cannot be 1, which is a ratio between the leading coefficient here, right? Therefore, we have another horizontal asymptote at y equals 1. And also we know when x is 5, this function is 0. So the horizontal asymptote is here. And when x is 0, this function is 5/2, which is here. Therefore, we know the graph of this function should be something like this, right? And there is a hole on the graph of this function, which is x cannot be 1. So 1 is probably here, right? So the graph of the function looks like this. And at this point, the function is discontinuous. And actually, you can remove this discontinuity by defining this function at this point. Therefore, this discontinuity is called removable discontinuity. Okay. Any questions? Okay, if no questions, let's consider another example. So this time I'll give you 5 minutes to think about this question here. What is the limit of this function as x approaches -3? Okay, can you hear me actually?
Yes.
Okay. Okay, have you finished? Okay, let's have a look at how we can solve this problem. So here, we know the function is actually a fraction between two polynomial functions, right? Therefore, this function is a rational function. Rational function is continuous at any point that is defined. So if you directly insert x equals -3 into that function, you will get something like -3 plus 1 squared minus 4 over 0, right? Which again will have a 0 over 0. this function apparently is not defined at x equals -3, right? This cannot be determined. Therefore, we cannot directly insert x equals 3 into that expression. So first of all, we need to consider how if we can simplify this expression. So original expression is equivalent to this one. So the limit of this function as x approaches -3. So first, let's expand 1 plus x squared. This will give us x squared plus 2x plus 1 minus 4 over x plus 3, right? And this equals limit as x approaches -3. So when you solve this question, do not forget to write the limit here, okay? You have to keep the limit symbol in each step. So that's x squared plus 2x minus 3 over x plus 3, right? So next, the numerator can be factorized to x plus 3 times x minus 1 over x plus 3, right? Therefore, as x approaches -3, that means x is a number that is close to -3 but cannot be -3. Therefore, x plus 3 is not 0. Therefore, we can cancel these two expressions. That equals the limit of x minus 1 when x approaches -3. So now we can insert x equals 3 into that expression. So the limit of this expression as x approaches -3 is just -3 minus 1, which is -4, right? So the correct answer is -4. Any questions? Any questions? No? Okay, then let's consider another practice. Again, evaluate the limit of this function as x approaches 0. Okay, again, I'll give you 5 minutes to think about this question by yourself. All right, have you finished? Okay, let's have a look at the solution together. Okay, again, if you directly insert x equals 0 to this expression, you will get something like 0 over 0, right? Again, this is indeterminate. Indeterminate because we don't know what the value it is, right? Because this function is simply not defined at x equals 0. So first of all, let's consider if we can simplify this function first. So that equals the limit of this function as x approaches 0. Okay, so note here we can try to rationalize the numerator, right? For example, we can times square root of 4 plus x plus 2 to both the numerator and denominator. And this will give us this expression here. And this equals the limit of this function as x approaches 0. So in the numerator, we have a plus b times a minus b. That equals a squared minus b squared, right? So that will give us a squared, which is square root of 4 plus x squared, minus b squared, which is 4. And let's just keep the denominator unchanged. Because this time when x approaches 0, the denominator won't be 0, right? Okay, that equals the limit of the function 4 plus x minus 4. Over x times square root of 4 plus x plus 2, which equals limit of x approaches 0, x over x times the square root of 4 plus x plus 2, right? When x approaches 0, that means x is close to 0, but x is not 0. Therefore, we can cancel the 2x here. That actually equals the limit of this function as x approaches 0, right? So now we have a ratio between two elementary functions. And we know this function is actually continuous at any point that is defined. Therefore, we can just insert x equals 0 to this function to evaluate this limit at this point. So if we insert x0 here, that's actually 1 over square root of 4 plus 2, which is 1 over 2 plus 2 equals 1/4. So the correct answer of the limit of this function as x approaches 0 is 1 over 4, right? Do you understand? Any questions? Okay, so have a look at the solution of this question here, okay? And if you have done so, we can take a 10 minutes break. Please return before 10 o'clock. Okay, so let's continue where we left off. Next, let's have a look at the properties of limit. We can use these properties to help us evaluate the limit of a function at a certain point. So here, let's assume that the limit of fx as x approaches a and the limit of gx as x approaches a both exist, and c is any constant. Then we have the following list of properties. First, the limit of a constant number c is equal to the constant c itself. Second, the limit of x as x approaches a is equal to a. Next, the limit of a sum of two functions is the sum of the limits of the two functions. And similarly, we have the limit of difference of the two functions is the difference of the limits of the two functions. And next, the limit of a constant times a function is the constant times the limit of this function. Next, the limit of a product of two functions is the product of the limits of the two functions. And similarly, we have the limit of the quotient of the two functions is the quotient of the limits of the two functions, provided that the denominator does not equal 0. Next, the limit of a power of a function is the power of the limit of this function, provided that the exponent is a rational number. Next, the limit of a root is a root of the limit, provided that the root exists. And last, we have the limit of composition of a function. Suppose that the limit of gx when x approaches a equals L, and the limit of fx as x approaches L is fl. Then we say the limit of f of g of x when x approaches a equals fl. Okay, so these are the limit properties we can use to evaluate the limit of a function at a given point. Any questions? Again, the proof of such properties involves the definition of limit. Actually, the more rigorous way to define the limit using the epsilon sigma statement, right? We haven't explored that in depth. So the proof of such properties are not covered in this course. If you are interested, I can give you the link to the reading materials you can have to after this class. Okay, so next, let's have a look at how we can use such properties to help us to evaluate the limit of a given function. So now let's consider this practice here. Given that the limit of fx as x approaches 2 equals 3, and the limit of gx as x approaches 2 equals 4, the limit of hx as x approaches 2 is 5. Can you evaluate the limit of the product of fx times gx, then plus hx as x approaches 2? I'll give you 5 minutes to think about the question here, okay? Okay, have you finished? Okay, let's have a look at the solution together. According to the properties of limits, we have the following solution here. First, the limit of a sum of two functions equals the limit of the function and then sum, right? The sum of the limits of functions. Therefore, original expression equals the limit of the product of fx times gx as x approaches 2 plus the limit of hx as x approaches 2. And that equals, according to the property that the limit of a product of two functions equals the limit of one function equals the limit of another function times the limit of another function, the former part equals the limit of fx times the limit of gx plus the limit of hx, right? Because we know the limit of fx when x approaches 2 is 3, the limit of gx is 4, the limit of hx is 5. So we can just plug these numbers in. Therefore, the limit of the composite function, the limit of the original function equals 3 times 4 plus 5, which is 17. Any questions? No? Okay, then let's have a look at how we can apply limits to analyze a business problem. So this is a real world problem that involves limits. So let's have a look at this example here. The manager of a coffee bean cafe determines that the demand for a new flavor of coffee is modeled by the function dp, where p represents the price of one cup in dollars, and d is the number of cups of coffee sold at that price. dp is given by this expression. When p is greater than 0 and less than or equal to 4, dp equals 16 over p squared. If p is more than 4, then dp equals 0. So that simply means if the price is greater than 4, probably dollars, then there will be no one who wants to buy the coffee, right? Question A, determine the value of each limit if it exists. First, the limit of uppercase D of P when P approaches 4 from negative side. Second, the limit of dP as P approaches 4 from the right side. Then the limit of dP as P approaches 4. Question B, interpret the meaning of these limits. Okay, I'll give you 5 minutes to think about this question by yourself. And then after that, we'll have a look at the solution together. All right, have you finished? Let's have a look at the solution together. First, to determine the left-hand limit, we can use a function definition for p less than 4, or dp equals 16 over p squared, right? The limit of dp1, p approaches 4 from left side equals the limit of 16 over p squared, which equals 16 over 4 squared, right? Because when p approaches 4 from the left side, that means p must be smaller than 4. Therefore, we should use this expression here. So if we insert 4 to 16 over p squared, then we'll get the limit of this function equals 1. Next, to determine the right-hand limit, we should use the function definition for p is greater than 4, right? So the limit of dp as p approaches 4 from the right side means we should consider a value that is close to 0 and is greater than 0, right? Therefore, we should use the other expression 0. So that means the limit of dp as p approaches 4 from the right side equals the limit of 0 as p approaches 4 from the right side. Of course, this is a constant number, then the limit of this constant number is 0. Question 3, because the left side of dp, the left limit of dp does not equal the right limit of dp as p approaches 4. Therefore, the limit of dp as p approaches 4 does not exist, because simply the left limit does not equal the right limit, right? Okay, question B. The limit of dp equals 1 as p approaches 4 from the left side simply means that as the price of the coffee approaches 4 from the left side, the number of coffees sold approaches 1. On the other hand, when the limit of the function dp as p approaches 4 from the right side equals 0 means that when the price of the coffee is greater than 4, no matter how close p approaches 4 from the right side, no coffees are sold. You understand? Any questions? Okay, if you have no questions, let's do a quick summary by revisiting our learning goals for today. So after this lesson, now you should be able to understand the definition of one-sided continuity of a function at a point. Then understand the definition of continuity of a function on an interval, whether it's open interval or a closed interval. We have learned the concept of continuity on open interval yesterday, right? And today we have learned the definition of continuity of a function on a closed interval. Then recognize common functions that are known to be continuous. So basically, all elementary functions are continuous at any point where they are defined, and you should be familiar with the concept of elementary functions. So be careful with the concept here, okay? You can use this conclusion to help us to evaluate the limit of a function, of a elementary function at a certain point. And next, you should also be able to use function continuity and limit properties to algebraically evaluate one-sided limits or limit, if exists, of a function at a certain point. And then last, apply limits to analyze real-world problems. Okay, so that concludes today's lesson. If you have any questions, you can leave me a message. Otherwise, you can start doing today's homework. I'll upload today's homework to our Google Classroom. Okay.